Okay, so this is a pretty short topic called isotopes. Now, in the last unit, we talked about how to draw an atom, and I mentioned that the atomic mass is not a whole number, and that we would talk soon about why it's not a whole number, why it has so many numbers after that decimal point. And the reason is that many atoms exist in multiple forms, which means that they have differing numbers of neutrons, which changes the mass of that atom. Now remember, the identity of an atom has to do with its protons. So as long as we leave the proton number the same, we still have the same element. Now, what you see here is a hydrogen atom. I did not put the thing from the periodic table there, but the atomic mass of hydrogen is 1 point blah, 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 blah. So that tells us that we have one proton, no neutrons, and one electron. This is the most common form of hydrogen. However, sometimes hydrogen exists with an atomic mass of 2, which means that it has a proton and a neutron. This is referred to as an isotope of hydrogen. Still have one electron because it has to be neutral. So all we're doing here is changing the mass. Now, hydrogen also has a third isotope, which has 2 neutrons in addition to the proton, which means that its atomic mass is 3. So these are 3 isotopes of hydrogen. Now, when we calculate the atomic mass of any element, we are taking the average mass of all of the atoms of that element in the universe. And what we see is that most of the hydrogen exists in this form. So the number on the periodic table is closest to 1, the atomic mass of this isotope. But it's not an even one because there are small quantities of this isotope and this isotope that exist. And therefore, the mass of the element, the average mass of the element around the universe, is slightly higher than 1. If this were the most common isotope, then the atomic mass that we saw in the periodic table would be closest to the number 2. Anyway, this is why we round the numbers, so that we end up with the most common form of the isotope. And by the way, this we just call hydrogen. This one's called deuterium. This one's called tritium. For any of you that are history buffs, you may know something about the manufacturing of nuclear weapons, the atomic bomb, which involved deuterium to a great degree. I won't go into that. So, like I was saying, the atomic mass of an element is the average mass of all the isotopes. So here's hydrogen on the periodic table, 1.0079. And so that tells us that most of the atoms in that element, or most of the hydrogen atoms, take this form. Now, some isotopes are less stable than others. For hydrogen, this is the most stable isotope, which is why most of the hydrogen atoms take this form. Deuterium and tritium are less stable. And when an atom or an isotope is not perfectly stable, it tries to become stable. In this case, tritium would try to become more stable by getting rid of one of its neutrons. Deuterium would try to become more stable by getting rid of its one neutron. So both of these are trying to get back to the more stable form of the isotope. And when a neutron leaves, this is called, let me move my picture, radioactive decay. Sometimes it's just the neutron leaving. Sometimes a neutron bumps into an electron and the electron leaves. Sometimes the neutron bumps into a proton and the proton leaves. Every isotope is a little different in terms of how it becomes more stable. But this radioactive decay is predictable and, as it turns out, very useful. So, radioactive decay or radiation is used by all kinds of things in science and medicine. You're, of course, familiar with taking x rays. That's a type of radioactivity. And you may not be aware, but the reason that we know what the shape of a DNA molecule looks like is because of radiation. The list of things that we use radiation for is too long to cover in this unit. But fundamentally, it comes from the concept that atoms exist in different isotopes. One of those isotopes is more stable than the others. And in the effort for unstable isotopes to become stable, they emit energy or radioactive decay that we can use.